Hello, MET 200 students. This is Dr. Hamid Isazadeh. One of the manufacturing processes is casting, and here in the lecture 11, we cover the fundamental of the casting processes and also cover some of the um, casting that are in the industry. And because this topic is pretty long, so we split it into two sections. If you look at the content section of the book, um, we will be covering chapter 10, Fundamental of Metal Casting, and then in chapter 11, we will discuss the various metal casting processes like sand casting, like expandable mold casting processes, and then permanent mold casting, um, and the quality of the casting process. And we try to cover these topics as much as possible. In the fundamental of metal casting, we cover these three subsection overview of the casting technology and how we can, heat and pour the metal, pour the hot metal into the, mold, and how metal is going to be solidified. Cooling process is also important. Solidification and cooling the metal from um, melting point to room temperature will affect the quality of the metal, the cast metal. What is casting process? Casting is a manufacturing process where we have a liquid material, hot metal, which is in liquid, state. Then that liquid is going to be poured into a mold. The mold has a hollow cavity. So the cavity is in desired shape. It depends on the application, it depends on your design. So you will have different shape in that mold. Then we allow the hot metal to solidify, and then the solidified part is called casting. And after that, the part can be ejected, or the mold can be broken in a way that we will obtain the solidified part out of it. And solidification process can be classified according to their material are being used. One is metal, ceramic, and polymers. So casting can be performed on these materials. As you see in this chart, we have a three classification for metal, glass for glass, and polymers. But in this lecture, we are focusing mostly on the metal part, and the top part here, where we have two subcategory for the metals: expandable mold casting, and then we have permanent mold casting. In the expandable mold casting, then we have the mold uh, composed of sand material. Also, we have other type of expandable mold casting. We try to cover this section. What are the capabilities and advantages of metal casting? The metal casting can create a complex part geometry, such as this, example. This one is a die-cast aluminum transmission housing, and this one is um, a trio of rings produced by investment casting. Another benefit or advantage of metal casting is that it can create uh, external and internal features. Look at this example, the bottom one. We have engine block. So engine block, as you know, it has several cylinders location. This one has four. Um, so these cylinders are internal features. So this um, process, this manufacturing process, can make those internal feature. And next advantage is that this one, the process can be net shape or sometimes near net shape. What is a net shape? Net shape means when the part is made by the casting process, it does not require additional processes like machining or any other manufacturing processes. Another way to say it, it does not need post process. So the part is somehow ready to be used in the manufacturing or for the end user. And with this technique, with this technology, we can produce very large parts. That is another advantage. And some casting methods are very good choice for mass production because when you make the mold, uh, especially the permanent mold, uh, then you can make a lot of material, a lot of samples um, without destroying, without going from one mold to another mold. So it saves uh, a lot of time, a lot of cost for the um, manufacturer. So in terms of big parts, we have engine block, head of automotive, vehicle, wood burning, a stove, and pump housing. Also, this process can be used for a small part like a dental crown, jewelry, a small statue, and frying pans. These are some of examples for the small part. Like any other manufacturing processes, there are some disadvantages for casting, and these disadvantages can be different for different casting process. One problem that we have in casting is that it has a low mechanical property. So the strength is low for some of the casting. You need to use additional manufacturing process, or it's called heat treatment, where the strength can be enhanced, improved as needed. Another problem, especially for sand casting, uh, is that the dimension accuracy. If you have a poor dimension accuracy, the surface finish is rough. Depending on the application, if you need high accuracy, then machining process is recommended. The next disadvantage is that it has a safety hazard for the workers, as because we are working with hot metal, hot molten metal. The next problem with casting is it has environmental issues that have to be, has to be taken care of. Here we have some terminology for the casting. The casting is usually performed in the foundry, and that foundry we have equipment for making molds, for melting the metal and handling the molten metal. We have equipment for performing the casting process, and we have equipment for cleaning the finished casting. And the person who work in the foundry is called foundryman, And the process has several steps. Heating the metal. Um, so the heating metal is done by a furnace, which is heat the metal to the molten temperature, and the heat that we need is sum of three section, three portion. One heat, certain amount of heat is needed to raise the temperature to melting point, and we have some energy, some heat for fusion. So the metal is going to be converted, it's going to be transformed from solid to metal or liquid, and then we need some heat to raise the molten metal to desired temperature for pouring section. Here we have additional step after solidification shown in this graph. This part of the slide, we have a trimming that is required for some parts. We have to for example, we have multiple samples, in one casting process. Then the parts are connected to each other. So we have to remove them from each other. So trimming is one process. And if we have core, next slide I'll discuss. Sometimes we need core to make an internal feature. Then we have to make surface, do some surface cleaning if we need a high accuracy on the external features. We have to see inspection. We have to do some inspection on the part. If there are some issues, then we have to do repair. And heat treatment is another post process that can increase the mechanical property of the casted part. In the casting process, we have various form of mold. Some of them are open mold, some of them are closed mold. Here we have these two molds, as I mentioned, open, and this is closed mold. And the molds have cavity, and the geometry of that cavity determines the part shape. And the cavity should be designed in a way that it is larger than the actual part. Why is that? Why the part has to be larger than the actual cast metal? The reason is that metal will shrink, right? So when they are in the liquid form, in the molten state, they are larger, in larger size. Then when they cool down to room temperature, we have contraction, and this part has to be taken into account. So when the part is solidified, it has the desired size and feature. And the molds are made of various materials like sand, plaster, ceramic, and metal. Here is the answer for the question, which I said already. We need a larger size for the cavity to allow for shrinkage and metal during the solidification process. We have two categories for casting process. One is called expandable mold process, where we have an expandable mold, and the mold is going to be destroyed in order to remove the casting or the part. The mold material is sand, plaster, plus binders. Then we have a permanent mold process where we use a permanent mold to produce a mini casting. So it is used for large production. And the mold is made of metal. It is possible that we use ceramic refractory material for the mold, the permanent mold process. And there are some advantages and disadvantages for each process. If you want to make an intricate geometry, you should go with the expandable mold process, because later on then you can destroy the part and then obtain the casting. The part shape in permanent mold process is limited um, because we need to open the mold, and the permanent mold process is more economic when we have large production, since the mold is not we don't need to change it, so we will keep the mold for many days, for many parts. Because of that reason, um, it's going to be cost effective comparing with the expandable mold process, where you need to make a mold for every single part. But this is not the case for permanent mold process. Here in this slide we have the terminology for sand casting process. In the sand casting we have two halves, as you see in this picture. This is the upper half, and this is the bottom half. And the upper half is called cope, and the bottom half is called drag. And then these upper mold is inside flask. The box around the mold is called flask, and here this section we have parting line. Then we have a pouring cup where the material is going to be poured in this mold. And this is the part. We have a riser next to the part, and then this part is called down sprue, and this is flask mold. So as you see, we have core here. So some parts requires internal feature, and then we use core. So the core will be taken out. We have to destroy the core after once the part is done. Some of them are will be evaporated. And here we have a riser. This section, the riser, we have hot metal there. When you pour the metal, some of them goes, some of them stay here. Why is that? The main reason is that once the material contract, so we need a bank of the metals. So that metal is going to be supplied during contraction, during solidification. So the part has enough metal for the metal cast in that cavity. Here we have a slide that shows the process for making a mold cavity in the sand casting process. In the sand casting, we would need a pattern, which is similar to the actual part that we need, the metal cast part. The pattern is oversized, So, this is important because it allows for the shrinkage during solidification, and the pattern make an external feature of the cast part. So you place the pattern. So pattern is a prototype. You place it in the sand, and the sand will pick up the external the shape of that pattern, and then once you make the cavity with that pattern, the pattern is going to be removed. Sometimes you need the geometry is complex. You would need some internal feature. Then you use core like this one. This is a cylinder. It makes the internal feature for you. Sand should be sand in the mold is moist and has some binder, so it can maintain the shape, so it doesn't fall apart. As I mentioned earlier, we need a core for the internal surfaces, and the core makes it is made of sand material and some binder to make to keep that shape. And after the process, once the part is cooled down to room temperature, we need to remove the core from the part. And there are various methods to do this step. Um, some of them, when the process is done, you can shake the part, and that core can be um, taken out easily, as you shake it, as you shake the part. So it's some of them you place in the machine, so the machine vibrate and do shaking and vibration. So then the part is that core is going to be broken. The gating system in the casting process consists of a down sprue, which is here. Then we have a runner, which connects the down sprue to the main cavity. Then we have a pouring cup. The pouring cup is important because it can minimize the splash or turbulence that may happen when the hot metal is poured into the cavity. Next part is riser. Riser is a reservoir in the mold, which is a source of liquid metal to compensate for the shrinkage that occurs during solidification. And the reservoir or the riser must be designed in a way that the material inside of it is going to freeze after the main casting. This is important because it can, if it is in the liquid form, then it can supply sufficient material to the main cavity. Otherwise, then it is not useful. There are a couple notes about the riser. The riser is a waste material. Once the part is done, the process is done, it can be remelted, then can be reused. If we can minimize this unit in order to save energy and save material. Here we have a plot that shows the solidification over time. This part of the graph, we have temperature. Here we have time. Then it shows the solidification process for a pure metal. Pure metal has different behavior compared to alloy. So here, when material is cooled down, it gets to freezing point, so where the freezing is going to start, and then at the same temperature, um, the freezing is going to continue. More material is going to be transformed to liquid. The temperature doesn't change, it's going to stay flat, but we need some time, so it requires some uh, amount of time for transformation to take place. After this point, the metal is completely solid, then the solid is going to go down to room temperature. This is a schematic that shows you um, grain structure in pure metal. So here we have the wall of the mold from up to bottom all the way to this section, and we have a characteristic which is called chilling action. The chilling action makes some small grain behavior near the wall, because we have very rapidly um, cooling action around the wall. As we mentioned before, if we have a rapid cooling, then the grain won't have time to get larger, so we will have a small grain. So this is something that happens near the wall. Around the wall, near the this wall, we have a small grains. Then a little further from the wall, we have a long grain, which are columnar. They are called columnar grain, which is oriented toward the center of casting. In most casting processes, we are working with the alloys. And as you know, alloys is a combination of several elements. Here we have one alloy of nickel with copper, and it shows that if you have pure nickel, the temperature for melting or solidification is 1 point, which is here at this point. The same thing for copper. The temperature for solidification or melting of copper is 1083 degrees Celsius. But if you have 50% copper or with 50% nickel, the solidification is not a flat line. Solidification starts at this point. It will be completed at this temperature. So here's the temperature. This shows the solidification curvature in the pure alloy, pure metal. We had a flat line, but now we don't have the flat line anymore. So this is the curvature for this is solidification curvature for alloys. So it's more complex compared to pure metal. One big issue in the alloy that we face is a segregation of alloying elements. So we have that first, we have that chilling effect near the wall. As you see, this area we have a small grain size because of they are cooling fast, so they don't have time to become larger. And then after that skin, we start to get in larger grain, or columnar grain, because that cooling process is going to be longer. But here in the center, we have some alloying element that are not fixed, that are not mixed with this columnar grains. The main reason is that some of the elements, for example, copper and nickel, um, some of them have a lower melting temperature, some of them have higher melting temperature. Because of that, that is one example. That because of that characteristic, these metals, this alloy, will settle in the center of the part. Here in this schematic, we have three cast structures for metals. The first one on the left, we have pure metal. We mentioned that we have a skinning effect or chilling effect in the wall, near the wall, so the grains are small. And then further inside, we have a columnar. This is the um, alloy. We have the similar issue around the wall, and then inside near the center, we have um, a smaller grain. The grain are um, in similar size. They are called equiax zone. And when we make some casting part, we would like to have consistency. So the parts, all the parts should have the same grain structure, grain morphology. The texture should be the same. We don't we don't want actually inconsistency. If you there are some methods, some resolution to fix this problem. One of them is using a nucleating agent. Or inoculant. When you add those elements, so the material will start to solidify together, so the inoculation start all over the place at the same time. Then you will have a better morphology that you may need for a certain application. Solidification time. This time can be calculate. Can we can calculate this value based on some of the uh, parameters. So this time tells us how much time, how much how long it will take for the casting to solidify when we put it into that pouring cup. Um, the total time is T in this equation, TS, and the equation is called Cherepanov rule. Um, V is the volume of the casting. For example, this part, the volume of that part has to be calculated. Then the surface area of that casting also needs to be calculated and then plug into this equation. Then we have an exponent with the typical value of number 2. And then we have a mold constant, which is dependent on mold material, thermal property of the casting metal, and pouring temperature relative to the melting point. What type of information we get from this rule? Chevarnov rule. It tells us a casting with a higher volume to surface area cools and solidifies more slowly than one with a lower ratio. The equation was T C V over A to the power of 2. If the volume over A goes up, the amount of time is going to be the amount of time required to cool is going to be larger. And here is one example. If you have a tube, a long tube, compared to a tube with shorter, if we do calculation, we will find that the longer tube has a larger area. And this one has lower surface area. So the volume is going to be the same, but that one has a larger surface area. That means that the time required for this part to solidify is going to be less. So it cools faster. But for this one, it cools, faster. It cools slower because the time goes up, the time for a cooling process, right? This is important because we can use this, equation to find the volume to area ratio for the riser. Because we want the riser solidifies after the part, so it should be still in liquid form when the part is gonna be solidified. So we need it, in a liquid form. So if you want to have the riser in liquid, state, you should have a volume to area ratio with a lower value. With a lower value, it means the area should be small. Volume, if volume is, stay the same, doesn't change, you should make it. You should make this area smaller, like this example. And instead of having a long feature, make it more compact feature. Then it minimizes the effects of shrinkage during cooling process. Let's go to the processes. There are 3 categories for the metal casting processes: sand casting, other expandable mold casting processes, permanent mold casting process. But in this lecture, we will look at 2 categories: the expandable mold casting and permanent mold process. In the expandable mold process, mold is going to be sacrificed for the part. So the mold is going to be removed when the solidification is completed. It has advantages and disadvantages. With this expandable mold process, we can make parts with a complex geometry. The problem with that process is that the production rate is going to be limited by the time to make mold rather than casting itself. So that is the drawback of the expandable mold process. In the permanent mold process, mold is made of metal and it can be used to make many casting. A good thing about it, you can have higher production rate. The problem with that, geometries are limited because we need to open the mold. So we don't have we cannot make a very complex part with the permanent mold processes. Here is the overview of sand casting. We mentioned before that we have a pouring cup, this part, or pouring basin, and then we have a gate, and then we have a runner which goes to the cavity, mold cavity. We may have some core to make an internal feature. We have riser or metal reservoir. This process is very well known in the industry, and this can be used for steel. We can use it for nickel, titanium, for high melting, temperature material, and it can make part from a small to a very large part. So that is a very good thing about this process. You can make a very big part, and that is not possible with other casting processes. Here we have one case industrial pump that was made with the sand casting process. You see some of the features were machined in order to have a good high accuracy, and most of the outside surface, external surface, they were not machined, so the quality, the surface will be sufficient for that job. Here are the steps in the sand casting process. We have to pour the molten metal into the sand mold. Then we have to provide time for metal to solidify. The time depends on that parameter, the volume to surface ratio, and other parameters that we mentioned. And then we have to break up the mold to remove the casting, do some cleaning and inspection, and separate the gating and riser system from the part. And last is going to be heat treatment of the casting. If we need some improved property, mechanical property, if you want to change microstructure, if you need to change grain size from small to large, or large to small, this kind of changing, manipulating to the microstructure can be done through heat treatment process. Here are the steps for making the sand mold. Here, this you see the raw material is going to be melted, then it's going to be poured into the sand mold, solidification. But then in the mold preparation, we have to make some mixture of sand with a binder, and then if we may need core, so we have to make core. If we need pattern, that pattern has to be made. Then all of them pattern, core, and sand will be used to make that mold. Then the mold is going to be placed here for pouring the metal into the mold, and then we have solidification and so on. Here are some points about the pattern. The pattern are some parts that we need for the making the cavity inside the mold, and they are a little oversized for the shrinkage and machining allowance purposes. And the pattern can be wood, can be metal, it can be plastic, and type of pattern in sand casting are solid pattern. This one, it can be a split pattern, it can be match plate pattern, and this is the cope and drag pattern. As you mentioned before, core is needed in some application, in some casting process to make internal um, feature. So the core has to be placed in the cavity in one way, and some of them can be supported with the chaplet, like this part as you see in this picture. There are some properties for the mold that we need to consider. For example, the strength has to be considered. The mold has to have a good amount of strength to maintain the shape and resist the erosion. And permeability is important to it allow the hot air escape and pass through voids in the sand. And thermal stability is another factor that should be considered. It is um, if, if you have a good, a high thermal stability, it can resist, the mold can resist cracking in contact with the molten metal. The next one is a collapsibility, or ability to give way and allow casting to shrink without cracking the casting. Last one is reusability. Um, can we use the sand again, we reuse it for other mold? That is important, because if you can use the sand for the next process, for the next round, it save cost for the manufacturer. Uh, for the sand, we also need some specific properties. In the sand, we use silica SiO2. Sometimes we mix it with other mineral. The sand should have a good refractory property for high temperature use. If you use a small grain size for the sand, it gives you better surface finish on the part. If you use large grain size in the for the sand, then the mold is going to be permeable. It allows the gas to escape. If you use irregular grain shape for the sand, it makes the mold stronger, say very strong, so it doesn't crack, because they interlock to each other, the grains, compared to the round grain. The disadvantage is that um, if you use irregular grain, it reduces the permeability, so the gas will stay inside um, the cavity. We use the binder in the foundry sand, so the sand is going to be held together by a mixture of water, bonding clay, like 90% sand, then we have 3% water, then there is 7% clay. And other agents might be used, organic resin, uh, or inorganic binder like a sodium silicate. We may use additive combination with this material to increase the strength or the permeability. There are three types of sand mold. One is a green sand mold, which has a mixture of sand, clay, and water. The word green means the mold contains moisture at the time of pouring process. The next one is dry sand mold, where we have organic binder rather than clay, and the mold is baked to improve the strength. The last one is skin dry mold, where we dry the mold cavity surface um, for certain depths, for example, 10 to 25 millimeter. We use torches, heating lamp to dry the surface of the mold. In the next lecture, we talk about other expandable mold process, such as shell molding, expanded polystyrene process, and investment casting process.